Radar remote sensing has progressed tremendously over the past several decades and used in diverse applications such as air traffic control, defense, autonomous driving, and weather monitoring. A commonly used system is the pulse Doppler radar, which is capable of transmitting pulses toward targets and determines their presence, location, and Doppler velocity from the reflected signals. Radar system design is a challenging task that suffers from many trade-offs. For example, high-range resolution radar needs large signal bandwidths. A second trade-off is between the dwell time and the Doppler resolution. To detect fast-moving targets, long dwell times are required. However, long dwell times imply that the radar is unable to scan quickly towards other directions. Another design trade-off involves angular or spatial resolution and the number of antennas in radar antenna arrays. Higher spatial resolution is achieved by using more antenna elements, but it also increases the size and cost of the system. This is why we created a new technology based upon a novel approach in sampling theory called exampling. Our exampling-based sub-Nyquist radar prototype detects targets using signals sampled below the Nyquist rate. In the exampling framework, only the content of a few narrow bands is sampled and processed by the radar receiver. The parameters of the received analog signal are embodied in its Fourier coefficients. Using our 4-channel sampler card, multi-channel analog processing and low-rate sampling scheme are used to extract spectral information for specific frequency bands. The Fourier coefficient calculation is then performed digitally after sampling to reconstruct the signal. A typical radar signal scenario consists of targets, clutter, and noise. The composite signal is then sampled at a low rate via exampling. Our advanced processing method then recovers the delayed Doppler map of detected targets using only the low-rate samples. Our method is robust to the presence of noise and clutter. The reconstructed target seen has the same resolution as if it were sampled at a high rate, thereby breaking the link between bandwidth and range resolution. Our technique paves the way for a cognitive radar which shares its spectrum with other communication services without any degradation in performance. We transmit only in those narrow frequency subbands that are sampled by the sub-Nyquist radar receiver, allowing the holes to be used by other comm services. The radar transmit power is now focused in narrow bands, leading to an enhanced signal-to-noise ratio. In our cognitive radar prototype, the waveform generator limits the transmit signal to only 4 narrow subbands. For example, here the radar signal is transmitted in 4 different subbands in the spectrum shared with other services. The transmit power in these 4 bands is higher than a wideband radar signal. The received signal in the antenna is sampled only in 4 subbands by the sub-Nyquist radar receiver to produce a delayed Doppler of detected targets without loss of resolution. We now consider breaking the link between the dwell time and Doppler resolution by decreasing the time on target through interleaved transmission of a few pulses in different directions. For example, here the targets lie in 2 different directions. The radar collects the return signal from each direction after non-uniform transmission of pulses. Our advanced joint processing then recovers the ranges and Doppler velocities of targets in both directions at a native Doppler resolution, but shorter dwell time. We now show reducing numbers of antennas without losing spatial resolution in a multiple input, multiple output radar. A MIMO radar uses an array of several transmit and receive antenna elements, with each transmitter radiating a different waveform. Our sub-Nyquist techniques can be applied in spatial domain to recover the target azimuth using thinned antenna arrays. To this spatial sub-Nyquist MIMO, we add temporal sub-Nyquist sampling at each received element. Further, each transmit element uses only few narrow subbands and is, therefore, cognitive. Our cognitive sub-Nyquist MIMO hardware prototype demonstrates spatial and temporal sub-Nyquist samplings for several array configurations. The prototype's cognitive sub-Nyquist 4x5 MIMO array reduces the combined spectral and temporal sampling rate by 87.5% and performs better than the non-cognitive Nyquist 8x10 array for a given target scenario. In conclusion, using sampling, it is finally possible to break the link between the signal bandwidth and radar range resolution, dwell time and Doppler resolution, number of antennas and angular resolution, and finally, enable coexistence in spectrally crowded environments.